Welcome back to Physics 142 Online. We're now going to start talking about how to analyze the motion of charges using energy methods. You might remember from the first semester of the course, we looked at how to analyze the motion of masses under the influence of forces using Newton's laws. But then we came up with an alternate way of analyzing those kinds of problems using methods of energy, and especially the conservation of energy. So today, let's look at how charges behave in the presence of external forces, and we'll be able to define a potential energy for charges in the presence of electric fields, and that will also lead to the definition of something called the electric potential. So first of all, let's just review what the definition is of potential energy change. And the potential energy of an object changes when work is done on that object by some external force against another force. So, for example, gravity. The force of gravity pulls down on an object when it's near the Earth's surface, so that if we apply a force in the opposite direction to oppose the force of gravity, and we move the object from some initial to some final point, we're changing its potential energy. You see here in the sketch, if we raise an object from the ground at point A up to point B by applying an external force F that's equal to the weight, so we move the object upward, we're increasing its potential energy. And the formulas are pretty simple. If the force is it moves the object very slowly, then basically the acceleration is zero, so that the upward force is the same as the downward force of gravity. And we look at the integral of F dot dl, because that gives us the work done by the force, and the force vector is upward with a magnitude mg. The dl vector, the infinitesimal displacement, is also upward with a magnitude dy, and so the dot product of those two vectors, since they're parallel, is just mg times dy. The mg comes outside the integral, and so going from point A to B involves a change in the height from 0 to h, so that this integral just becomes h. So the change in potential energy from point A to point B, the final being point B and the initial being point A, is just mgh. And we derived this equation back in the first semester of the course. We can now do something very similar for a charge in the presence of an electric field. But before we do that, let's just show how we usually define the zero value, because potential energy differences are defined in this way. We always have to pick a zero somewhere, and so in the case of gravitational potential energy, we often pick the zero to be at the surface of the Earth. And so when we do that, we say that the potential energy at point B, which is at a height h above the surface of the Earth, is just mgh. So now, what if we have an electric field E that is pointing from left to right here, and so of course a charge Q would feel a force QE. But now let's apply an opposite force, an external force, moving against the force from the electric field, and we're going to move the object from point B to point A, and that's going to be a charge Q. So if the charge moves very slowly, then the net force is zero, so that this force F is equal and opposite to the force from the field QE, and that means that the force that the external person is applying is minus QE. Therefore, we can calculate the potential energy change as it moves from point B to point A. F dot dl here becomes negative QE dot dl. The Q comes outside, and we have the E dot dl term, so that the potential energy change, UA minus UB, is minus Q times this integral. And if we imagined moving the object to point A from some point that's infinitely far away, so we'd be saying what's going to be the potential energy of the object at point A with respect to an infinite point far away, it would look like this. And this becomes the reference point for most electrical potential energy problems. We pick at an infinite distance, we say that the potential energy is equal to zero. So you bring the object from an infinite distance into some final point A, set the potential energy equal to zero at infinity, and so we get that the potential energy is equal to to minus q times this integral, starting at infinity, moving into some final point a, of E dot dl. Now, what is that quantity, that integral quantity? It's interesting because in terms of the units, it's equal to the potential energy per unit charge that the charge has at point A. And as a result of that, we will often define that quantity to have a certain kind of meaning. As I said, it's the work done or the potential energy per unit charge. So if we divide both sides by Q here, we get this quantity V, which is the electric potential. Note that potential energy depends on the charge Q, but dividing both sides by Q gives us this quantity V, which only depends on the electric field and the initial and the final points. So this electric potential is a potential energy per unit charge. What are the units of it? Well, it's pretty easy to see that E has units of newtons per coulomb, dl has units of meters, so electric potential is Newton meter per coulomb. And as a result of this, then, we can look at a point A and say that there's a simple relationship between the electric potential energy of a charge at that point and the electric potential at that point. So if we're going to set the potential energy equal to 0 at infinity, then we can relate the two at that point by saying that the potential energy is just Q times the potential. So now what if we want to move a charge between 2 points, B and A? We know that the electric potential at point A, we've already written down that it's equal to minus this integral from infinity to A of E dot dl. And let's imagine moving the charge from infinity to A, but going through a point B along the way. So this integral would be broken down into 2 pieces, because we would start at infinity and go to B first, and then go from B to A, the final location. So this just expands the integral into 2 terms. So V at point A then is just given by these 2 terms, but we distribute the minus sign through there because that minus sign was originally out in front of the original integral. So from that we can identify that the first term looks exactly like the term did for the potential at point A, except it's with reference to point B. So what we see is that the potential at point A is equal to the potential at point B minus this additional term that takes us from B to A. So just rearranging this by subtracting VB from both sides, or by writing V sub A equal to VB minus this integral from B to A, and then subtracting B from both sides, we get that the potential difference between points A and B is just equal to this single integral that takes you from B to A, E dot dl, or if we want to get rid of the minus sign, we can interchange the order of integration. So we're saying that the difference in electric potential from point B to point A is equal to minus this integral from B to A of E dot dl. So another way of thinking about this is that we can write down the work done in moving the charge through a potential difference as the work done is equal to Q times the change in the electric potential. I'm continuing our discussion of electric potential and electric potential differences between 2 points. So you see on the screen the definition that we obtained for electric potential difference between 2 points A and B. And this is the kind of equation that we'll use when we want to find, we're given an electric field, we know what the electric field is in a region, and we want to know the difference in potential between points A and B. In this sketch you can see they're separated by a distance d. And what makes this example simple is that the electric field is uniform. It's got the same magnitude and direction everywhere in space. So we start from the definition and we need to simplify the integral. And so we know the direction of E, and in this case E and dl are parallel. Now what is dl? I've had students come in and say, what is this dl quantity anyway? dl is a tiny displacement vector. It's in the direction that we're moving when we go from point A to B. So dl
is like, if it were along the x direction, we would call it dx. But the direction is important too, and so we would attach I hat to it if it were in the x direction. So here, E and dl are parallel, so that we just write down E times dl, the magnitude of E times the magnitude of dl. The dot product goes away because it would involve the cosine of 0, which is 1. This makes the resulting integral very easy to solve, so VA minus VB is integral from a to b of E dl. Since E is uniform, it can come outside the integral. All along the path of integration, it's got the same value. So what's left is E times integral from a to b of dl. That just adds up all of the tiny vectors pointing from a to b, and actually adds up all their magnitudes, all the magnitudes of those vectors pointing from a to b, and the sum is simply the distance d. So VA minus VB equals ED. It's a very simple result that comes in this special case. Now the question that arises is, which point is a higher potential? And you have some homework problems that ask this very same question once you're done with the calculation. So you can see, well, the right-hand side of this result is positive because it only depends on the magnitude of E and the magnitude of D, and those are both positive numbers. So that means VA is higher than VB, therefore A is at a higher potential than B. Okay? And what this actually tells us is that there's a general principle, and this is good to remember, that when you move along an electric field line, you're always moving downhill in potential. You're always moving from higher to lower potential when you follow a field line. And this equation here also shows us that there's another way we could write down the units for electric field. Before, when we were using Coulomb's law, we wrote down electric field as newtons per coulomb in terms of force, right? In this case, we can see that if I solve for electric field in this equation, I would get the units for potential difference divided by the units for length, or volts per meter. So volts per meter are the same as newtons per coulomb, just expressed in slightly different ways. All right, now let's do a more interesting case, which involves the calculation of the electric potential due to a point charge. And we're going to actually find the value of the electric potential at a special point, or at a particular point, because we will use the reference point of infinity. And it makes sense that if you get infinitely far away from a point charge, its influence on you should be very small. So that will be, as r goes to infinity, that's where we're going to define the electric potential to be 0. So that's why we write down V at point P, it's equal to minus the integral from the reference point, which here is infinity, to final point P of E dot dl. So when we're done here, we'll use the electric field that we know a point charge has to do this calculation, and then we'll know an expression for the electric potential a certain distance r away from a point charge. So we can also show, because of the kind of fields that we get for electric fields due to point charges, we know that this result is path independent. So no matter what path I pick to do the integral, starting off at infinity and moving into point P, I will get the same answer. And if that's true, then I will choose the simplest possible path, the path that'll make this integral easiest to calculate. So we'll start at infinity and we'll come in along the radial direction until we get to a point P, along a field line. And that makes the calculation easy. So from our study of Coulomb's law, we found the electric field of a point charge has this standard form, kq over r squared in the r hat direction. dl, remember I said it's a tiny displacement vector. So if my path is going to be along the radial direction, then dl is a vector that has magnitude dr, because it's along the radial direction, times r hat. So E dot dl, well, we see E and dl are parallel again, right? But the important thing in this case, and what makes it a little bit more interesting, is that E is not constant. As we move in from infinity to the final point P, the strength of E is changing because it depends on 1 over the distance squared. So we're actually going to have to perform an honest-to-goodness integral. So we take the equation for potential at point P, plug in the electric field vector, plug in the dl vector, the dot product of r hat and r hat is just 1, right? So we're left with kq dr over r squared. And the kq are constants that can come outside the integral. So minus kq, integral from infinity to r of dr over r squared. And we know how to do that integral. That's an easy integral to do. That just gives us negative 1 over r, evaluated between r and infinity. So the two minus signs cancel, and we get kq. And evaluating this expression at the upper and lower limits, we have kq times 1 over r minus 1 over infinity. And of course that doesn't look proper, but this simply reflects the fact that we have called infinity our reference point, and we've set the 0 of potential there, because 1 over infinity goes to 0, right? So we're left with a very simple result. The electric potential at a point P for a point charge is kq over r. Now electric potential, remember, does not have a direction. It's a scalar, not a vector. It can have a plus or minus sign, and it will, depending on whether this point charge is positive or negative. So V can be positive or negative, but it does not have a direction associated with it, which makes the very next thing much easier. Let's say we have not a single point charge, but a collection of point charges. And I want to know, at some point P, what is the electric potential? Well, electric potential, just like electric field, follows the superposition principle, but it's even easier to add up electric potentials because they don't have directions. So if I want to know the net electric potential at point P, I would just write down the individual contributions from each of the charges. So for Q1, I get KQ1 over R1. For Q2, I get KQ2 over R2, and so on and so forth. So no matter how many point charges I have, I just keep adding terms. And these charges, Q1, Q2, Q3, and so on, they can be positive or negative. And so depending on their signs, that will influence the final value of the electric potential. But there's no directions. This makes working with electric potential much easier than working directly with electric field. So a simple shorthand expression for this is that find the electric potential by summing up the contributions of all of the point charges from 1 to n. Nice and easy. Okay? One last thing then that I'd like to introduce, and then in class we'll do some example calculations using all of this stuff. What about the energy that's stored? Imagine taking two charges, Q1 and Q2, and assume for the moment they're both positive. If I bring them in from far away into some final distance where they're R1, 2 apart from each other, well, if they're positive, then I had to do work to bring them in because they were repelling each other. As I was bringing them closer together, they were repelling each other. And so that required me to do work. That work is a form of stored potential energy. And if I release those two charges after I've brought them in and I let go of them, they'll fly away. And the energy that I put into the system, moving them together, will be recovered in the form of their kinetic energy. All right? So how can we write down an expression for that stored potential energy? And it's very easy. We first just imagine that we start off with a single charge, Q1. And what I'm going to do now is show how to do this calculation not just for two charges, but for three charges or for any number of charges. So the first thing, we've got nothing, and we bring in a charge Q1 from infinity. Well, if there's no other charges around it, that doesn't take any work, because I don't have to push against any kind of external force. So the first step is easy. There's no work required. But now, once I've got Q1 in place, now I bring in Q2 from infinitely far away. And when I do that, the potential at the final location where I bring it is KQ1 over R12. That's the potential due to charge 1 at the location of charge 2. Well, the work required, we showed before that the work you do is equal to the stored potential energy. So the work it takes, the stored potential energy, is just Q2 times the potential, right? So U is Q times V. We developed that equation several slides back. So the work done is now K times the product of the charges over the distance between them. That's the energy that's stored, the potential energy that's stored in Q1 and Q2 when I bring them to this final distance. All right, and now the last step is Q3. I now bring that in from infinity and put it in this final location shown in the diagram. So I bring Q3 in from infinity. The work I have to do is Q3 times the potential at that point. So I have to consider contributions to that potential from the 2 point charges that are already there. KQ1 over R13, that's the potential due to Q1 at the location of Q3. KQ2 over R23, that's the corresponding contribution to the potential from charge Q2. So I add those up, multiply by Q3, and I get these two terms here. KQ1Q3 over R13 plus KQ2Q3 over R23. And you can see what happens. When we're all done, I can add all three of these pieces together, W1, W2, and W3, to get the total work done, which means the total potential energy stored. And in practice, I always get the same number of terms as there are pairs of charges. So in the triangle, I've got 1 and 2, that's one pair. 1 and 3 is another pair. And 2 and 3 is a third pair. So I have 3 non-zero terms in my final expression. W, then, for this would be the sum of those 3 terms. W, the work I do, is the same as the potential energy I store. So again, it equals to the sum of those 3 terms. And a fancy way of writing this down is to show a double summation. And that double summation means pick a charge and then sum over all of the other charges that there are, as long as you don't double count. And so KQ1, Q2 over R12, that's of course the first term, and you'll have another term like that for every unique pair of charges in the configuration. So having an expression for stored potential energy is helpful, because what we're going to use this to do is answer questions like this. If I bring 2 charges together to some distance away from each other, and let's assume they're both positive, if I let them go from rest, what speed will they have when they get very far apart? You've got a couple homework problems like that, and I will use this expression for stored potential energy to do some examples in class. I'll see you in class.